Good morning, everybody. I'd like to start by thanking very much the organisers of this symposium for inviting me here. The invitation is greatly appreciated. And I must make a special mention of the wonderful hospitality we enjoyed last night. It was an absolutely super concert of accordion music, so thank you in particular to Alexei for that. And the party afterwards was unexpected and hugely enjoyable. So thank you for that. So the title I have on the screen is slightly different from what's in the abstract simply to expand, because the central idea here is a full quaternion solution of the small amplitude equations of a rigid body. So let me begin. Maybe there's one already in. Is this the controller?
Yes, yes, yes.
It's not working. Okay, so there's quite a lot on the presentation, probably more than I can cover in the time. So there's extra material in the presentation, which is on my website. I'll tell you how to get it in a moment. So there are some slides with quite small print. Don't worry, I don't expect you to read these. They're simply there for later access if you wish to look at them. So I'm going to consider the dynamics of an eccentric sphere. So all through the talk I'll speak specifically of spherical bodies, nothing other than spheres. Okay, but the distribution of mass within the sphere is non-uniform. So the center of mass in general will not be at the geometric center. And this is the rock and roller. I'll define it more explicitly in a moment. Now, Alexei asked me if I could bring this rock and roller here, but it is a bowling ball with the top cut off, several kilos in weight. And I didn't fancy paying excess baggage and dropping it on other passengers' toes and so on. So the best I could do, well, one of the best was to bring a movie. Because I want to draw your attention to a certain type of motion of this body. So we tip it over and let it go. It's moving more or less in a straight line at the beginning. Let go, there she goes. So it's rocking back and forth, but as you see, it's also precessing. I'm not holding the camera very steady. Okay, it precesses around through an angle, but lo and behold, after a while, it changes its mind and precesses back again. Okay, so that's a curious behavior. So what I call recession is reversal of precession.
Here's a question like a question.
Sorry. Is that different from the usual rattleback that one sees that's elongated in one direction?
Yes, because first of all, this is a spherical body. The rattleback depends on two things, on the non-sphericity and also on friction.
But I can make a symmetric one and simply weight it asymmetric. I don't know, you said that the spin force.
Both ways.
I guess I don't know.
The rattleback normally, I mean, the actual body itself is not a pure ellipsoid.
But you can certainly make an ellipsoidal one, and by putting a weight in one direction or the other.
Oh, yeah, I've seen it in boats with...
It'll reverse one way. I don't know if it'll always continue, but I didn't know if this would continue either.
Yeah, please.
Bowling balls, when you buy them, they have weird weights on the inside. Is your bowling ball before you cut it, a spherical bowling ball, or is it a bowling ball with weird weights on the inside?
And to the best that we can evaluate, it's symmetric. We can't really determine the asymmetry, but there is obviously some asymmetry.
So they put some in on purpose or something.
Oh yeah, that's a different question. No, that's biased. This is not deliberately biased. Okay, I mean, to show you another example, let me go back to the presentation. As I say, I couldn't very well carry the bowling ball, but I hunted around on the web and found this candle holder from Copenhagen. So I brought one of these along, and it's more or less the same idea. it's spherical, roughly spherical. I can actually feel slight irregularities. It's more or less spherical. So I try to make this do the same. So I try to make it oscillate towards you and see what happens. So it's a matter of prayer at this stage. Okay, it's gone so far to here. It seems to have stopped. Let me show you on the website the numerical simulation of that. So I should say, if you want to find this stuff, if you Google for Peter Lynch, you find this very rich guy. He's a multi-millionaire. That ain't me. But I'm somewhere there to find me easily enough. And then this material is there, and you can click on the rock and roller. So what you see on the right is what you see in the physical rock and roller. What you see on the left is a numerical simulation of the body with the slight irregularity, and the trace of the point of contact is indicated here. You see the way it precesses around. Looks like it's a constant angle of precession. It's getting a little smaller now. Now it's stopped precessing, and now it will go the other way. So that's the phenomenon I call recession. And we're trying to understand that in some dynamically intuitive way. Let's go back. I think this clicker is jet lagged. Yes. Okay, I want to change the subject slightly here and talk about two types of orbit, box orbits and loop orbits, that come up in a wide range of physical systems. And this is a globular cluster. It's not a galaxy, it's much smaller, maybe 100,000 stars. And we want to consider how a star might move in this system. And astronomers, astrodynamicists, have identified these two types of orbit, box orbits, which cover a region simply connected, and loop orbits, which are multiply connected and stay away from the center of the cluster. These illustrations are from Binney and Tremaine, which is an excellent book on galactic dynamics came out a few years ago. So box orbits and loop orbits seem to be generic, because we find them also in the rock and roller, and we'd like to know why and under which conditions they occur. And then, what's the simplest physical system that could have such a distinction of orbits? And it turns out, if we look at a perturbed simple harmonic oscillator, we can get these two types of solution. So I looked at this, when I say I should have identified at the beginning my co-author, Miguel Bustamante, who's also in Dublin. We've done this work together. So here's the Lagrangian of a simple harmonic oscillator in two dimensions with the same frequency in each dimension. But if I now perturb it in these two ways, the first perturbation breaks the symmetry of the system, gives slightly different frequency in each direction. And the second perturbation, size epsilon, stiffens the system in a radially symmetric way. But obviously this will lead to nonlinear equations. So we can solve that. Well, that's a complicated system, but how do we solve it? We solve it by some perturbation method. My own favorite is average Lagrangian. So we have the Lagrangian, we average it with respect to the fast motion. So we assume solutions here which have a fast component. I see why this is not advancing, the battery is not good. We have a fast component and a slowly varying amplitude.
Double layer, triple layer.
Oh no, I won't try and change it now, it's not a good idea. Okay, if we average the Lagrangian and introduce new variables, which I won't define explicitly, we get two equations, effectively an amplitude and phase. And they are actually the canonical equations of the Hamiltonian here. So we can look at the solutions, and they depend on a parameter lambda. So there's a single parameter which depends on the two sides of the two perturbations in this way. we can get different types of solution depending on the size of lambda. So this is for small lambda and for lambda greater than 1. So for small lambda, you can see all the solutions are of the same character, whereas for lambda greater than 1, we have a separatrix, some sort of bifurcation at lambda equals 1, and we have two different types of solution. And in fact, these are box orbits, and these are loop orbits. And you can easily calculate them for this system, and you've seen them already. So we can get this distinction between two different types of solution in a rather simple example, this perturbed harmonic oscillator. So let's now try to characterize the rigid bodies that I'm looking at. And this picture is more of a suggestion than some sort of dogmatic statement. I don't know really what's the best way to describe these bodies. But some of the ones I look at, first of all, we will have a parameter A, which gives the distance between the geometric center and the center of mass. That could be 0, and it is 0 in the concentric Chaplegan sphere. It could be non-zero, and we might have the route sphere, or we might have the rock and roller. I haven't time to describe everything, but the two bodies I'm mainly concerned with are the rock and roller and the route sphere. And the difference between them is that for the route sphere we have a symmetry. We have two moments of inertia which are equal to each other, whereas that symmetry is broken in the rock and roller. Now a more general body is possible, which I've called here the Chaplegan sphere, but I don't know if that's the correct name. I hope to learn from you here just what Chaplegan did. But this body would have, the speciality of the rock and roller is that the geometric center is on a principal axis. So that's what I denote by this quantity delta. It's the angle between the principal axis, one of the principal axes, and the line from the center of mass to the geometric center. Okay, so I mainly discuss these two bodies.
This is I2, I3.
Yeah, they're the moments of inertia.
But in yours, you have two that are equal to each other. That's symmetric object. So you're talking about the inequality of the third one.
No, sorry. There's an I3, which I haven't written, which is equal to neither of these. Okay, so for the route sphere, two are equal, but the third is not.
Isn't that true for yours?
No, for the rock and roller, they're all unequal.
But just looking at that object.
Yes, that's right. But this is a physical body. Nothing is equal in a physical body. There's a small inequality, and that's the point. If this symmetry is broken, even in a very, very small way, 10 to the minus 4, this will change the entire character of the motion. In fact, I'll show you now two pictures.
So
here,
CC has these four.
well,
Okay.
let me go back. That's concentric Chaplegan sphere, because I don't know if this is an appropriate name. Maybe you can tell me what exactly Chaplegan did. I know he certainly studied and analyzed this body in pretty much complete detail. But whether he considered the general body, I don't know. But that's why I don't want to be dogmatic here. So this is really the case where the two centers coincide. It's concentric. Okay, where am I? Yes, this is the trace of the point of contact for the route sphere. So we have the symmetry here, two moments of inertia equal. Now if we break that symmetry even in a very small way, we get a trace something like this. It's totally different. And this is what you're seeing more or less on the table. This body and the bowling ball, they do not precess in a regular way. They either come back or they speed up and slow down their precession. And even the smallest perturbation is enough to change the character of the motion. That's why I think it's interesting. When I saw this first, I was amazed and just felt I have to try and understand this. And that's the main objective of the talk. Okay, that's Chaplegan, but I certainly don't propose to tell you about him. I'm here to learn rather than to preach about him. I think he appears to have done many very interesting things. I'll skip over that. So we'll go straight to the physical body now. So the rock and roller is a spherical rigid body with an asymmetric mass distribution. notice there is a relation with the tippy top, but I don't want to go into that. It'll draw me too far away. Let me a moment. Okay. Just for simplicity, I'll take unit mass and unit radius. That's no loss of generality. A denotes the distance between the center of mass and the center of symmetry of the body, center of the sphere. And the moments of inertia will be like this. I1 and I2 will be close together, or in the case of the round sphere, equal, and I3 will generally be larger than them. So we can write down Newton's equations that we all know and love, and there's nothing too difficult about that. At the beginning, I will use the Euler angles, so you know about them. And of course, we can talk about the angular velocity and angular momentum in the rotating frame. And with all that, we can write down the equations of motion. Now, this is a rotating frame. For historical reasons, I have a different rotation rate for the frame, but we needn't worry about the difference between large omega and small omega. We can take them to be equal for the purposes of this talk. So we have equations of motion here. Of course, it's easier to write down the Lagrangian, and then straight away we write down the equations of motion. So theta now is a vector with the 3 Euler angles, and omega is a vector with the 3 angular velocities. I'm not giving explicit forms for these matrices, but of course we know them. But the one important fact is that these matrices, well, this is a vector in the matrix, do not depend on the azimuthal angle phi. So there is a symmetry for all these bodies. Is it? Yes?
So to finish your sentence, but you are showing this as if it's a rolling thing, but you're writing this down as if it's maybe frictionless, it looks like. Is that right?
Oh, no, it's rolling. There's a rolling constraint.
But then don't you have trouble with Lagrange equations?
We have to do something about that. So, of course, there are non-holonomic constraints. If there were holonomic constraints, we could add a term to the Lagrangian, but this does not work for non-holonomic constraints. And it's interesting, there is some, this is the word I emphasize, misunderstandings about non-holonomic constraints. In fact, if you look in the standard textbook of Goldstein, Safko, and Poole, the discussion there is not correct. And there's an interesting exchange on the web about that. So even today, there are sometimes there's a lack of clarity. There's an interesting paper about non-holonomic constraints by Flannery in the American Journal of Physics, The Enigma of Non-Holonomic Constraints. So the title immediately suggests there's something puzzling here. So we can actually write the equations in this way. Now, Andy, is the answer to your question. There's an extra in here to take into account the constraints. Of course, they're in there. Okay, moving on now. Rout studied the symmetric body some time ago. This is the 6th edition of his book. Came out in 1905. And that discusses that. And he solved the problem in pretty much complete detail. He's taking this case, this is the important point, there's a symmetry here. The energy is obviously conserved because I'm not taking into account any kind of damping. And he also found 2 other constants. One is called Gellot's constant, which looks like a component of angular momentum, but it's not quite that, because R is the distance between the point of contact and the center of mass, and it's moving around. This is not a component of angular momentum, it's something more complicated. Okay, and there's another constant which is also slightly mystifying. It involves one component of angular velocity multiplied by a density function here, divided by a density function at density. And that's known as Rout's constant. But for the symmetric body, we now have 3 constants. Okay, let's skip that. Here's Rout and here's Gellot. Just briefly a little about both. Rout did the amazing thing of beating James Clerk Maxwell into 2nd place in the tripos in Cambridge in 1854. He was quite an achiever. Poor old Maxwell, you know, he wasn't so smart, was he? Well, of course, the tripos were a real grind. It wasn't really a question of smartness. It was drilling and speed. So I think Maxwell had a much more illustrious career. And then something very brief on Gellett. As I say, this can be read by you later. He was born in Tipperary. He was, for our purposes, he studied the theory of friction, made some advances there. He was the president of the Royal Irish Academy and provost of Trinity College, Dublin. Now, back to the ranch. We can solve the round sphere because we have a constant which immediately gives us omega 3. The initial conditions will give us this. Now we can get omega 2 from the Gellett constant, and now we can write the system in this way as an equation for theta, which in principle can be integrated. So it's an integrable system. Okay? And you notice that omega 2 and omega 3 are functions of the tilt angle. So that means when it's at maximum tilt, it's going in a certain way and it cannot be recessing. So there's no recession in the round sphere. What about the rock and roller? Well, all we have that is obviously constant energy, but we also have this symmetry, which is a little bit, it's intriguing and infuriating. As we think of Noether's theorem, we say, oh, there's a symmetry, there must be a constant, but we don't know that. It's non-holonomic. We have no guarantee that there's a constant. I don't know of any such.
Can you explain what the symmetry is?
Symmetry, yes. Okay. Wherever this body happens to be, let's say your x-axis in this direction, you change nothing by rotating the axis around. The azimuthal angle does not come into the problem.
So it's the symmetry of the room and the plane, not the object.
Yes, it's essentially a symmetry space, but it's, there's nothing in the system to distinguish the azimuthal angle. Now, so the point is, we haven't found such a missing constant. Maybe it's there, maybe it's not. Okay, but even though the constant, what I had called Gellett's and Routh's constants, I better now call them something else. I call them Gellett's and Routh's quantities. So these quantities are no longer constant, but we can use them and find out about the dynamics of the rock and roller. And in fact, we've been able to show that recession is related to these quantities passing through critical values. And that analysis is in the paper that I'll show in a moment. This is a diagram. One of the axes is the Gellett quantity, and the other is the Routh quantity. For the Routh sphere, we just have some point, fixed point. But for the rock and roller, that point will move around as the motion evolves. So we get patterns like this and can show that recession occurs when we cross one of these axes. That's all published already in a paper that's come out in JPhys A, so I won't dwell on it. And we can get various patterns of motion like this. And this, of course, looks like a classical box orbit. Okay, on now to the meat of the talk is to try and understand what's going on. Now, of course, the first thing you would think of doing is do a small amplitude analysis, try to do some sort of analysis about the point of equilibrium. In fact, looking at that, it's even sufficiently irregular that you can see that the top is sloping. It's not a very well manufactured candle holder. I wouldn't put it on my dinner table. But anyway, okay, the problem with the Euler angles is, of course, if you're at theta equals 0, maybe the North Pole, then theta may be small, but the other two angles are not small. And of course, as you pass through the pole, they change discontinuously. So all sorts of problems. We tried a perturbation analysis in Euler angles, but we just got nowhere. So we moved over then to use the Euler symmetric parameters. These are not blue. Hello?
Sorry. Am I allowed to ask?
Oh, certainly.
I mean, you could have picked different Euler angles that where the singularity was over on the side someplace instead of straight. You happen to pick Euler angles where the singularity is right at the center of interest.
It's an interesting idea, but would something be small then? I mean, the whole idea of the perturbation analysis is to be expanding for small theta. theta, if you pick other axis, let's say you put your North Pole on the equator, then theta is not going to be small anymore.
Subtract 5/2 or something.
Well, I'd say then you've just arrived back where we started. I mean, I don't dismiss the idea, but it's not obvious that it's going to work. Let's have a discussion on that later. I'm uneasy about the feasibility of that approach. Anyhow, these quantities are, it turns out, elements of a unit quaternion. So we write them, so gamma, zeta, psi, and eta, like this. This is a quaternion with unit amplitude. And these objects, of course, were introduced by William Rowan Hamilton in 1843. He spent many years agonizing over how to multiply them. He didn't know how to do it. Suddenly a flash of inspiration. They don't have to commute. They don't commute. That was his realization. That led on, of course, to an explosion of mathematical developments. And he was so excited that he scratched the formula I squared equals j squared, etc. equals -1 on a bridge by the canal in Dublin. And 100 years later, they put up this plaque to commemorate that. So these are these quantities. They have another name, Euler-Rodriguez parameters. We can, for example, express the angular velocities in terms of these, and so on. Now we're looking at small theta. So what happens when theta is small? Two of the quantities are of order 1, and 2 are of order theta. But the crux is nothing is singular. Everything is regular. We can go ahead. Okay. It comes out pretty quickly that omega-3 can be taken to be constant at first order in theta. That simplifies things greatly. We can immediately solve for 2 of these parameters as simply sinusoidal functions. And then the other 2 obey 2 second-order coupled differential equations. Not so simple, it's a bit of a tangle because the coefficients involve the other 2 and they're messed up and difficult to manage. But it turns out that a rather simple transformation, here we are, from xi and eta to mu and nu, using these quantities that we know, it's a time-dependent rotation, then the top 2 equations become the bottom 2 equations. And you see immediately they're much simpler because the coefficients, which I don't give explicitly, coefficients are constant, so we can immediately solve these. So now we have a complete solution of the small amplitude motion. We can look at this and see, does it do what we hope it will do? Okay, we can go through the motions. We look for a solution, sinusoidal solution. We can easily get out the eigenvalues and the eigenvectors here. And we have all of these in explicit form. I haven't told you what all these quantities k and omega are, but we know them. That's the point. So we have a full solution. And then from these equations, we have an immediate solution. And there are 2 components of the solution, one with amplitude mu1 and lambda1 mu1, and the other one with corresponding index 2 quantities. Right. I think my time may be short. Just to say, I mean, we can write a Lagrangian, of course, for this small amplitude system, and introduce generalized momenta, write a Hamiltonian, and that's not surprising. We've already integrated the system. Okay, and we can write down constants of motion. And we have, in terms of mu and mu, we have 2 constants. We can actually combine these to get the energy, so that's not surprising. So the energy and another constant, which is some sort of angular momentum quantity. Okay, but back again to the solution. This is the full solution now of the small amplitude motion. Now we're going to look at this. We take these 2 quantities here. This component of the motion is like this and like this. You see, of course, it's motion in an ellipse. And we know the speed or the angular velocity of that, because we know beta 1 is just the eigenvalue. And the other component is exactly the same with different parameters. And it happens to be, this will be a different sign, then this will be a different sign, so it'll spin in the opposite direction. So the solutions look like this. The inner, first component represents motion around this ellipse. Okay, and then we go to the center of that and take another ellipse moving around on the first one. And the point here moves anti-clockwise, and then the solution moves clockwise, because the eigenvalues are different signs. Okay? And then whatever the point is, it traces out a curve, like the black curve here. And the character of the solution then will depend on the relative sizes of these two ellipses. And we know them in terms of the parameters. You can see that in this case, because this ellipse is smaller than the other one, this point on this is never going to get to the center. So we have a loop orbit. Okay, things could be different. Things could be like that, with the second ellipse much larger. Okay, but then again, if you look at this carefully, you see it still can't get to the center. We still have a loop orbit. So what's going to be required is that the two ellipses are fairly close in size to each other. So that's a geometric requirement for the phenomenon of recession. And indeed, we can write this then algebraically. Recession will occur if and only if this inequality holds. And that will depend on the initial conditions and on the parameters of the body. So that completes that. I'm almost done. I'll just say a little about the round sphere, because you naturally ask, well, what happens to all this analysis if we restore the symmetry? But what happens then is we get the same solution, but now lambda, one of the lambdas is equal to 1, and one of the lambdas is equal to -1. So instead of two ellipses, we have two circles. Of course, we get, I think I'll skip this stuff, I've done it. We get two components of the motion. One is circular motion, clockwise, anti-clockwise circular motion, and one is clockwise circular motion. And that's how the solution can be described. So we have an inner circle here, and an outer circle then. So the center of the outer circle moves around the inner circle. And of course, the motion then is described by the point on the outer circle. Again, you'll see geometrically here, there's no chance for this black curve to reach the center. But what if the outer circle is smaller? Still again, you'll have different character of the motion, but it won't get the center. The only case in which it can access the center is if the two amplitudes are equal, and then it can go through the center, but it will go through the center every time. It won't recess. It won't go back and forward. Okay? So we've looked at a lot of other solutions. And of course, what you look at when you see the body, you don't really see the Euler angles. You see the motion of the center or the point of contact. So we have to connect that. The motion of the point of contact, just let me tell you, it's related, of course, directly. It emerges immediately. But it turns out the relationship between these parameters and the motion of the center is not entirely simple. But we've looked at that and described it. So my only job now is to thank you for your attention.
Any comments, questions?
Small comment. The book of Jarrett was first published in Dublin in 1870, and it was well before Pendlever issued his book in 1895. But in this book of Jarrett, there were certain paradoxical situation of dry friction included. And this book was then translated to German and published maybe about 1880 by Turner, and no other editions, as far as I know, exist, except of here in Ижевsk Udmurtian University. It was translated to Russian and published 2 years ago by our chairman Alexei Borisov. And maybe other participants would like to present their works to be translated to Russian and published here in Ижевsk. Yeah. But I got a small question. As far as I know, the Jarrett constant is can be applied in situations where sliding occurs, and direction of this sliding is well defined. But I suggest it couldn't be applied to the rolling systems. Jared constant.
Oh, my understanding is it's actually constant for both. It's more general than only for rolling systems. It actually holds for sliding systems. It certainly does hold, but I think Jared's contribution was to find this quantity in a sliding system, the system of sliding fish. I have to confess I have not read his book in either English or Russian. Maybe I should do so.
I believe it was published in Dublin.
Sorry, but I for 19.
May I recommend this?
$19.
We have no time for...
No, I'd like to answer his question.
Very quickly, very quickly.
This Jared constant is a projection of kinetic momentum onto a radius vector from the center mass to the point of contact, and it is a constant when the friction force is horizontal, because the friction force has only horizontal momentum, and therefore this projection remains constant when the gliding occurs or not.
Okay. Thank you very much for very impressive talk.
Can I ask one more question?
Your talk next. Okay.
We can sit a couple of minutes more.
Yeah, you can skip some of my talk. Several things you said in this rolling problem reminded me just of a rigid body in space. And I guess people don't like that problem because they know the solution and they can write it out in detail. But for example, the structural instability of the solution to the small perturbation in the I1 and I2 is common with the rigid body in space. And I wonder, do you have, in that whole mess of that complicated rigid body in space solution, is there this separation of box orbits and loop orbits?
I can't answer. I don't actually know the answer. I imagine almost certainly yes.
I mean, I think people stopped paying attention because they wrote big formulas, and so they said the problem was solved. But maybe this is hidden in those formulas. You think so?
I would be surprised if we didn't see this distinction in that problem. You can avoid writing big formulas by, geometric mechanics formulas, but never expand them later on into big formulas. And I just end by leaving this as a gift for Alexei.
They'll fill it with vodka and give it back to you.
Thank you very much for this gift.